So Peter, the square root of 4 is, and the square root of 100 is 10. And you would call those what? Perfect squares, yeah. So they're perfect squares that they can break down nicely without anything left over. The square root of 200. How would we do the square root of 200, Peter?
We break it up into the square root of 1 and the square root of 2.
Yeah. So if it isn't a perfect square, then we try and break it down into a number that is a perfect square, and that leftover piece stays underneath the radical. So this becomes 10, and then the square root of 2. So the perfect square part becomes the 10, and then we have the square root of 2. Jack, how about the square root of 72? What goes into 72?
6 square root of 2.
Yeah, so we would have 36 and 2. You want the biggest perfect square. Yes, 9 goes into 72, but 9 isn't the biggest. So it's kind of like the GCF, greatest common factor. We want to pick the biggest perfect square. So 36 is the biggest number. That's a perfect square that goes into 72. And that's 6 square roots of 2. So there's a couple vocab terms underneath, and then a little chart down below that kind of gives us properties to simplify radicals. And we're just going to work through some examples. But a radical doesn't just have to be a square root. So I put a little n on the symbol, and then I have an a underneath. That n usually is a square root, but it doesn't always have to be. So that n could change into a 3, a 4, a 5, a 6. It could be anything. We'll stop at 6. But that little n can be pretty much anything. So if you look at the 3 terms underneath, the radical is pretty much the whole thing. The whole problem is called a radical. Does anybody know what the radicand is? Nick? Yeah, so the radicand is the number underneath the square root. I have an a there just to represent any number. So the number under the square root or under the radical symbol. So it actually gets a name. It's called a radicand. So whatever number's underneath. Or it could be a letter too. What do you think the index is? Jack? The n. So the index is the n part. So if it's a 2, if I just have a square root of 5, we don't write the 2 there. The 2 is implied. But once it changes to a cube root of 5, then I have a number sitting there. But you don't ever put a 2 in there to represent a square root. The symbol implies that it's a square root. Anything beyond that, you would see then a number. And then the nth root of a number is taking that n and evaluating it. So we'll say evaluating the radical using the index. So actually breaking it down. Whatever the index is, that's called the nth root of a number, breaking that number down. And then the last 2 terms here, we kind of applied the perfect square above. We have a perfect cube. Josh, how would you explain a perfect square? Okay, so he said a number, when you square it, it gives you a whole number. Gavin? Yeah, that's perfect. A number multiplied by itself. Any number that can be multiplied by itself is a perfect square. So 2 times 2, 4 times 4, thank you. 8 times 8, whatever it happens to be. A number multiplied by itself. How would you then describe a perfect cube, Nina?
Number multiplied by itself twice.
Yeah, sure. Number multiplied by itself twice. of course, we could go on and on and on, but I think defining two of them, you get the idea. So perfect cubed is 2 times 2 times 2, not just 2 times 2. So at the bottom, there are two properties. And those properties help us break down or simplify radicals. And we have a product property, a quotient property, and then a power property. So 3 different properties. The first property looks a little weird because we have a couple different powers happening here, or exponents, numbers. But the n is the index. The m is the power of whatever is inside. And we can write that 2 different ways. So these are equivalent statements. So if I have a number to a power, I can pull that power outside and write it separate as well. So if you look, we have the cube root of 64. How else can I write 64? So what power could I write or change 64 into? Josh? 4 cubed. So the cube root of 64 is really the cube root of 4 cubed. And Josh, the cube root of 4 cubed is just 4. So these guys, the powers, because they're the same, they undo each other. Just like a square root undoes something that's squared. So a cube root undoes something that's cubed when the powers are the same. The second property is the multiplication property. So this is saying that if I have the same index, so if the little number on the chair of the radical is the same, then I can multiply those two values together. But they must be the same. So if I have a square root of 5 and a square root of 50, Michael, that would become the square root of, I said, yeah, square root of 10 is square root of 5. I guess I gave you the answer. And then, Michael, is there any way you can break down the square root of 50? 25 and 2, which we know is 5 square roots of 2. So if the index is the same, you're allowed to multiply them together. But they must be both square roots, both cube roots, both fourth roots. And then the last one works the same way with division. If I'm dividing two separate numbers, but the index is the same, we can actually kind of group that together and say we have one fraction that we're dividing. Or we could go the other way and we can separate it and look at two separate parts that we're dividing. And it just depends on which way works better for you to simplify the problem. But these go either way. So I can combine them together and make it one fraction underneath one square root. Or maybe it's better for me to separate them into two separate pieces of a fraction so that we can simplify. So Ava, this one, if we separate it, we can simplify it into, right. So separating into two pieces, thinking of the top part of the fraction and the bottom part so that we can simplify. And sometimes you would do one way, sometimes you do the other. It just kind of depends on what your numbers are. So if you flip the page, there are a ton of examples that I have there. I might have went a little overboard. I was doing these while Sadie was at piano lessons. So just plugging away. We're going to use the properties to simplify each expression. So our goal is to break this down into a smaller number, but not having a decimal. So keeping it still as a perfect square and a radical. So in letter A, we have the cube root of 4 and the cube root of 2. They're both cubed roots. When you multiply these together, Brady, you end up with the cube root of 8. All right. So here's where your little sheet helps, especially when the numbers get a little bigger. If you look in the cube root column, is 8 in that column? Does 8 have a perfect cube? Nina?
2.
Yeah, it's 2. So boom, 2. Done. The cube root of 8 is 2. Letter B, we have the square root of 5 squared. What does that become? Just 5. That's that undoing property. If I have a square root of 5 and it's squared, a square root and a square undo each other. And that's just 5. Another way you could think about that, that little 2 is actually squaring the 5. So I could really say this is the square root of 25. So the exponent really applies to the number. And that's why it cancels and it gets a value of 5 there. Letter C, we have the cube root of 5 and the cube root of 25. So cool, if I multiply those together, you get 125. And then what is the cube root of 125? Just 5, yeah. So you should see 125 in that list of your cube columns. And then the last one, the square root of 50 over the square root of 2. Ava.
5.
Yeah, so this really becomes 50 divided by 2, which is just 5. So there you can kind of think of that as one big division problem. Reduce those. So the square root of 50, square root of 2, I can actually divide them and get the square root of 25, which is just 5. The second group of problems one should again apply the properties, but it says we have indices other than 2. An indice is just the plural form of an index. So once it's bigger than 2, it's called an indice. It's a fancy name. But the index, the 3, or having a 4, or having a 5. So you might want to look at that little perfect worksheet. The power is a 3. And we have the cube root of 81. Your goal is to find a perfect cube that breaks into 81. And it has to be from that list. So just like square roots, it works the same way, except now we have a cube root. So from your cube list, what number in that list goes into 81? Jack? 27. 27 times what, Jack? So 27 times 3 makes 81. And then, Jack, the cube root of 27 is 3, and then we still have the cube root of 3. So it's the same as a square root, but we're using the cube root column now. So letter B says the fifth root of 32. So go into the power of 5s. What is the fifth root of 32, Peter? Just 2. That is a perfect fifth. 2 times 2 times 2 times 2 times 2 makes 32. So then looking at the next one, we have the fifth root of 128. So now you got to go to the power of 5s and see, do any of those numbers break into 128? Jack, any of those numbers go into 128?
32.
And 4. So all you do is you take 128 and you divide it by the numbers in the column. So divide it by 32. You could try 81, but 81 doesn't divide into 128. So Jack, this would simplify to become
2.
right, 2 and then the fifth root of 4. So again, same properties as a square root, but you're now using different numbers. And then the last one here, we have the fourth root of 81. Peter? Say it again. 3. So the fourth root of 81 is 3. Again, that's in your column of fourth powers. Questions? So there's some problems underneath. A lot. Probably too many. Like I said, I went a little crazy. So see if you can break a couple of those down. Looks like it gets more interesting down at like D. First couple I think are fairly straightforward. But you're trying to find a number that breaks into the value underneath the radical. And depending on the index, make sure you're using the correct column of numbers. So that sheet helps give you an idea of like what numbers you could try and use to divide into the value underneath the radical. So that sheet is very helpful for it. Brady, what'd you use for 32? Square root of 32.
The square root of 4. The square root of 8.
What two numbers go into 32?
Is 4 and 8 going?
Bigger. What else bigger than 4 and 8? Yes, 4 and 8.
16 and 2.
There you go. 16 and 2, so that's 4 square roots of 2. So, biggest number. Nina, how about the square root of 75?
Square root of 3 and square root of 25.
Yeah. And then the cube root of 16. JT, what about the cube root of 16? So 2 cube root of 2. And then the cube root of 135. Michael, what about 135? What goes into 135 that's in that cube column? Josh, what do you think? 27 goes into it? How many times? 5, yeah. So if you're not sure, take 135 and just start dividing by the numbers in the column. So divide it by 8 because that's the first cube. If that doesn't work, divide it by 27 because that's the next cube. So you want to divide it by those big numbers that you wrote. So 3 and then the cube root of 5. All right, so the fourth root of 48. So look at your fourth root column. And we're just looking for a number that's in that column that goes into 48. Gavin, do you know what number would go into 48? So then that becomes, nice. So 16 is a fourth root. 16 times 3 makes 48. For letter E, this looks like letter F looks a little different, but E is kind of similar to the ones that we just did. So again, you want to see what is a fifth or a perfect fifth that goes into 486. Peter? Say it again. 2. As I thought you said. 243 and 2. And 243, the fifth root of it is just 3. And then we have the fifth root of 2. So questions so far? If you look at letter F, we have the cube root of 27, and then it's to the fourth power. If you take 27 to the fourth power, it's a really big number. What is an easier way to simplify that? Michael? Yeah, you can cube 27 first. That little power can be written separately on the outside, and that was that first property. So you're allowed to separate the power and think of it last if it makes it easier for you to work through the problem. So Michael, you just said the cube root of 27 becomes 3. And then you still have the power of 4, and Michael, 3 to the fourth is 81. So when you have a power attached to a number, that power is allowed to separate, and it can be done first or it can be done last. So if you take 27 to the fourth power, it's huge. But instead, just work with the 27 first. Letter G, we have the cube or the square root of 3 cubed. How do you think you do that one, Jack?
I put the power of 3 in the...
Yeah, so this is kind of like the opposite of the one we just did. That's why they're next to each other. So The power can also go inside if it helps you. And Jack, the square root of 3 cubed is really the square root of, right. So it's the square root of 27, which is 9 and 3. And he said 3 square root 3. So it kind of depends on how is it going to benefit you to simplify the problem. So is it better to pull it out, or is it better to take it in and actually apply the power? Questions? So the bottom 4 are either the multiplication or the division property. How would you think about letter H? Ava, what do you think you'd do there with letter H?
I multiplied 4 and 2.
Yeah, so the numbers that are outside are like numbers.
And then 5
And 5 and
and 15.
15 would give you
75.
75. So the pieces that are the same, the outside numbers, the underneath. And then break it down. So Ava, if I break it down,
You can take it 25 and 3.
right. And then what do you do with the 8 outside? So the square root of 25 becomes
5.
5.
So you multiply 11
right. So the square root of 25 is 5. This 8 gets multiplied by that 5. Because right now it's being multiplied by the square root. So whatever number comes out of the square root, you multiply with the 8. So 40, and then the square root of 3. So multiply the outside numbers, multiply the inside numbers, simplify it, and then you just have to make sure you're multiplying by that 8. Letter I, we have the 5th root of 27 and the 5th root of 9. Nick, what is 27 times 9? 243, and the 5th root of 243 is 3. Sorry. And then the last two, what do you think you do for J? Nina, what do you do with J?
Divide 245 by 5.
Yeah, what do you get when you divide them?
49.
What is the square root of 49? 7. They're both square roots. You can divide them. Just like they're both square roots, you can multiply them. So then, Peter, we have the cube root of 192 divided by the cube root of 3. What did you say you got? And then the cube root of 64 is 4. Any questions so far?
So would that not cancel out the cubes?
The cubed doesn't cancel out when you divide. It stays with it. Good question. Really good question. So the cube part doesn't cancel. You're literally just dividing the numbers, but the index stays there. That's a really good question, Ava. So whatever that index is, it stays. It doesn't cancel. So we have a couple other problems, of course, on the next side. Got to make it a little more interesting because it is algebra. Algebra is variables. Can't just deal with numbers. We won't do all of these. We'll just do some of them. Again, I went crazy. Like tons of examples on there, just in case you needed extras. I guess this page doesn't have quite as many as the last one. So when you have variables, generally you're going to have the statement, assume all variables are positive. Because a variable is any number. And if you have a negative in place of a variable, we can't take the square root of a negative number. So that's why you'll see the simplify the following radicals, assume all variables are positive so that we can simplify it further. How do you think you simplify something with a variable? Jack? You just square root the variable. So I'm going to write this, and you don't have to write it like this all the time, but just to kind of show you what you're really thinking about. You're square rooting each piece. So I can separate them because this is the product property. It's being multiplied. Really, that means each one of those, each piece underneath, has a square root with it. So Jack, the square root of 36 is 6. What's the square root of x squared? And then the square root of y to the 4th is y. That's correct. square root of fourth, square root of y to the fourth, why does that become y squared? Okay. Yeah. So when you have a square root, remember there's a little 2 there. You're actually dividing when you have a square root. You're dividing exponents. So 2 divided by 2 is actually 1. 4 divided by 2 is 2. So when you have exponents attached to variables, you're actually dividing those exponents to simplify. So let's see if we can look at the next one, because of course the next one isn't quite as straightforward. So we have the square root of 18, the square root of x cubed, the square root of y to the 7th. You don't have to separate them, but sometimes it helps until you kind of get the idea. Look at each piece separately. So Dimitri, what could we do with the square root of 18? How would that one break down?
The square root of 9x cubed, y to the 7th, and the square root of 2.
Okay, and then the square root of, you said, square root of 9 is 3. And then I still have this square root of 2. So I'm just going to leave that there. That's the square root of 18. So if there's really a little 2 sitting here, and you're dividing, you can't really divide 3 by 2 evenly. So how does that work? So we have the square root of x cubed. Nick?
Pull out x and the square root of x.
Okay, so he said you pull out an x because 2 goes into 3 one time. And then what's your remainder? 1. So whatever is a remainder, whatever is left after you divide, goes underneath the square root. So I'm going to have 1 power of x left over. So let me talk about this again. 3 divided by 2. I can do that one time because 2 goes into 3 once with a remainder of 1. My remainder of 1 stays underneath. So let's look at the y. How many times does 2 go into 7? Peter, how many times does 2 go into 7? 3 times. So I'm going to have y cubed outside. Peter, what is left? What's your remainder? Just 1. So 2 goes into 7 3 times because 2 times 3 makes 6. The remainder stays underneath. So you got to think about a little old school division. Your remainder has to stay underneath. So outside we had the 3 because of the 18. I have x, y cubed. And then underneath we have 2x and y. You don't have to put the power of 1 up there, but I was just kind of reiterating that there's a remainder. Questions? A little different with variables. So looking at the next one, we're going to try and think about it the same way. If it helps you to separate them, it's okay to have them separate. So thinking about each piece. So the first part, the cube root of 27, the number's going to be easier to think about because it's a number. So Nina, what is the cube root of 27? 3. So that's 3. And then you have to do a little bit of division. So how many times does 3 go into 5? Ava, how many times does 3 go into 5? Once. So I pull an x out. What is left over when you take out those 3? 2. So 3 divides into 5 once with a remainder of 2. My remainder goes underneath. Ava, the next one is just the cube root of y cubed. 3 goes into 3 once. So I'm pulling out a y. And that's it. There's nothing left inside because the y divided evenly. So if it divides evenly, you shouldn't have a remainder because there's nothing left. So the last one under this is a 4th root. So 4th root of 32, maybe I'll write it underneath so I have more room. 4th 32, fourth root of x to the fifth, y to the eighth, and z to the sixth. So think about the 32 first. JT, how would we break down the fourth root of 32? Good. So the fourth root of 16 becomes 2. All right, so we got our 2. And then back here, I'm going to write the fourth root and put the 2 underneath it, because that's going to be my remainder part. So the next part, JT, 4 goes into 5 once with a remainder of 1. So there's my remainder part. The radical part is the remainder. JT, 4 goes into 8 twice. Is there a remainder? No. And then the last time, 4 goes into 6 once, and the remainder is 2. So the part that divided evenly, the part that's the remainder. Questions? See if we can do one more down here. Why don't we just do the first? Now let's do letter C. Letter C looks pretty nice. Cube root of 54, cube root of x 15, cube root of y 11. I'll get you a worksheet. Yeah. Jack, what goes into 54?
9 and
27 and 3?
2. Yeah,
Or 2, 27 and 2? No.
yeah, I just took it.
And then with a cube root of 27 is 3. Okay, so we've got a 3 there. And then Jack, 3 goes into 15. 3 goes into 15 5 times. No remainder. 3 goes into 11.
3 times.
And the remainder is 2.
Would you put the 2 from before 27?
Oh, I forgot to. Thanks. Appreciate that. Cole was getting me there too. Thanks for watching up for me. So there are 30 problems in here because I think the more you practice, the easier it'll get. And a lot of them do have the variables in them almost right away. The answers are posted in Google Classroom. Please check your answers. A few of you still might want to present a problem for tomorrow. So I have 19 and 25 and let's see, it's just Dimitri, Emma, Brady, Gavin, and Steven. Brady, 19, Emma, 25. So Brady 19, Emma 25. And I promise tomorrow will not be a whole period of notes. We'll do a couple examples with adding and subtracting.